How does NaF-Ap2O7 exist in two distinct crystal structures with I-NaF-Ap2O7 forming at low temperature and transforming into 2-NaF-Ap2O7 at a high temperature of 750 degrees Celsius? And what factors govern this phase transition? How do the structural characteristics differ between I-NaF-Ap2O7 and 2-NaF-Ap2O7, particularly considering that 2-NaF-Ap2O7 is composed of octahedral units of P2O4 and FeO3 sharing the same angle, and how does this unique configuration influence its stability and ion transport properties? Can Davis Zurins manufacture solid-state sodium-ion batteries made from seawater in Latvia? What insights can be gained from examining the crystal types presented in Figure 3.35a and the corresponding additional figure? And in what ways do these diagrams help in understanding the spatial arrangement and connectivity of the octahedral units? How does the utilization of the Fe superscript 2/Fe superscript 3 redox couple relate to the calculation of the theoretical specific capacity of 97 mod G superscript 1 for Na2Fe-P2O7? And what underlying electrochemical processes contribute to this capacity limit? Why does the measured charging capacity of Na2Fe-P2O7 reach as high as 130 mod G superscript 1, exceeding the theoretical value, and what factors, such as possible structural defects, additional redox activity, or kinetic effects, might account for this discrepancy? How might variations in the synthesis process, phase purity, or morphology of these sodium-based pyrophosphate materials impact the migration paths of sodium ions and the efficiency of the redox reactions within the material? In what ways does understanding these structural transformations and electrochemical nuances contribute to optimizing the performance of polyanionic compounds for sodium-ion batteries? And what further experimental investigations could help to clarify the mechanisms responsible for the enhanced charging capacity observed in Na2Fe-P2O7? How does the conversion of the Fe superscript 3/Fe redox couple at a potential as high as 5V lead to a measured capacity that is much higher than the theoretical specific capacity? And what limitations arise from the general electrolyte's maximum voltage window of about 4.5V that prevent charging to such high potentials? How does this high voltage redox mechanism affect the overall electrochemical performance of the material, and what practical issues does it raise for its use in sodium-ion batteries? How did researchers synthesize this material using conventional solid-state methods, and what insights can be drawn from the charge/discharge curve shown in Figure 3.35c? That demonstrates a reversible specific capacity reaching 90 Ma G superscript 1. In what way does the structure of Na2Fe-P2O7, which is composed of a framework built from FeO6 octahedra and FeO5 square pyramids completely separated by pyrophosphate groups, create effective open channels that enhance ion transport and overall rate performance, especially when compared with phosphoric acid-based materials? What?